we need to discuss how to take second derivatives with implicit differentiation. I know you are all excited to see that. Moaning, groaning. Okay, second derivatives. And if you know how to do second derivatives, then you'll also know how to do third derivatives, fourth derivatives, whatever you need. This is not a major topic in the section, but it's definitely something we all need to know. Okay, so let's see here. Going back to x squared plus y squared equals 25. So I'm just going to jump to the first derivative. We did this work previously. Obviously, there are some steps between these two, but we've seen that already. We know that the derivative here, dy over dx, equals negative x over y, following the steps from earlier. So how would we do or perform a second derivative? What would we do? What would we go? Okay, well, we would take it as normal based on this. And in this case, we would need a quotient rule. Okay, so here we go. And notice we're going to use that notation, the Leibniz notation for the second derivative. It's d squared y over dx squared. And here is the quotient rule, a low, d high minus high, d low is dy over dx all over the low squared. Okay, let's clean that up just a little bit. Now you might think, all right, we're good to go. That's the second derivative. We're not done with it yet. Here's the thing. Sure, we took another derivative, but now our second derivative involves a first derivative, dy over dx, and we don't like that. We can do better, turns out. Why don't we like that? Well, look at the first derivative. All it has is x and y. So if you told us a point, we could plug in the x value, the y value. We want to be able to do the same thing with the second derivative. If you tell me a value of x and y, I want to just have x's and y's here. I don't want to have this first derivative, okay? So here's what we'll do. What's nice is we know what that equals. dy over dx equals negative x over y. So we can substitute negative x over y in for that dy over dx. And then our second derivative will only be in terms of x and y. So in this case, what would that look like? Well, we're just going to put negative x over y right there. And we're going to clean this up. We do want to simplify this sort of thing. And then we'll have our second derivative. Okay, well, if we multiply that up, and okay, well, we'll just kind of ignore this part for a moment. We've got negative y minus x squared over y all over y squared. You think, a fraction inside of a fraction. We can simplify further. What should we do? Hey, let's multiply everything by a y. And then we won't have this fraction anymore. So if the y multiplies all around, it turns out to be this. Our second derivative, d squared y over dx squared equals negative y squared minus x squared over y to the third. And it's almost like we almost have that circle equation. Or it's like the negative of the circle. Ooh, that's surprising. It's kind of interesting. Okay. While we're talking about other things that have to do with implicit differentiation, let's chat about this. Now, this just came out of the blue. What is the derivative of inverse sine of x, or you might call it arc sine of x? Wait, what? Where did this come from? The derivative of arc sine x? Okay, so in a moment, we're going to know the derivative formulas for all 6 inverse trig functions. And implicit differentiation is going to help us do that. How is that? How is implicit differentiation going to help us with the inverse trigs? Okay, so check it out. So let's just think of it as y equals inverse sine of x, or arc sine x. What if we took the sine of both sides? The sine of y equals the sine of the arc sine of x. Well, these would cancel, right? The sine of the inverse sine, or cancel out, okay? So that first statement would be the same as the sine of y equals x. Okay, probably, maybe a good review for us, but how is this helping us get the derivative? Okay, so we took an explicit equation and we wrote it as an implicit equation. We have no idea what this derivative is, but now that it's implicit, we've got sine, and we do know what the derivative of this is. So we're going to use implicit differentiation here, and it's going to lead us back to what that, okay, you get it. Let's go for it. Applying implicit differentiation. Take the derivative of both. Okay, we've got a chain rule here, the sine of y. So it's going to be cosine y times dy over dx. Okay. And our derivative of x, of course, is just 1. All right. Then we can isolate the dy over dx if we divide this over. So starting from the top, y equals arc sine x, we found the derivative dy over dx equals 1 over cosine y. Interesting. Okay, well, in really a very similar theme for that second derivative, right? We weren't satisfied with it at first. We went and did a substitution. Same thing here. We are not satisfied with this way of expressing the derivative of inverse sine of x. Why is that? Okay, so back here, this is a function. Inverse sine of x, that is a legitimate function. We wrote it as an implicit, but it is a function. Okay, so whenever we have a function, we really want the derivative to be expressed in terms of x. We don't want it expressed in terms of y. We wanted the x value, right? That's how we normally do these things. That is. Okay, and we can get it. Okay, so here's my comment to summarize. That's okay, that's good, but we want this in terms of x. How are we going to get that? All right, well, let's see. So I'm going to pull up a familiar trig identity. Cos squared y plus sine squared y equals 1. That would have to be true, right? And we're using y, obviously, because we got a y there. What would happen if we solve for cosine y? If we isolate a cosine y? Isolating cosine y, so we should subtract sine squared y, and then, because it's a square, we should take a square root. If we solve for cosine y, wouldn't that be the square root of 1 minus sine squared y? Okay, sure. How is this helpful? This seems worse. Okay, because we know what the sine of y equals, right? From the beginning, way back here, okay, the sine of y is equal to x. So here, when we say sine squared y, that's really just x squared. Oh, man. So we just found that the cosine of y equals the square root of 1 minus x squared. This whole thing goes in for the denominator, and that's the derivative of inverse sine of x. 1 over the square root of 1 minus x squared. Okay, so we've proven this one. I'm just going to tell you the rest, save you the suspense. Here they are. The inverse trig derivatives. Let's talk through them. There's a lot of writing there. You might want to pause. Okay, so inverse sine of x, we just found 1 over the square root of 1 minus x squared. Turns out inverse cosine of x is the same thing, but negative. Weird. We could prove that by the same methods. Turns out inverse tangent of x does not involve a square root. It's 1 over 1 plus x squared. Okay. Inverse cosecant x, negative 1 over x square root x squared minus 1. So the two pieces inside the square root end up reversing, and then we get this other x there. Inverse secant of x, same thing, but positive. So it kind of keeps that theme, positive, negative. Secant is positive, cosecant's negative. And cotangent is the same as tangent, but negative. That's kind of nice. So again, all of the cos are the negatives. And we even see that relationship. Sine and cosine are identical, except the negative. Tangent and cotangent, cosecant and secant. So matched up with its co, you just think of the negative, how it works. So again, here, we just got to know these at the end of the day. I don't necessarily expect, well, I should back up. I do expect you to memorize these. You need to memorize these. The ones you really need to memorize are the first three. Let me say that. These come up by far the most, these derivatives, compared to these other ones. I'm talking about this class, but I'm also talking about Calc 2, Calc 3. These come up way more than these do. That's so be absolutely sure you have these memorized. But these aren't too bad once you know those, right? You just switch the thing and okay, there's an x and then that's just a negative. I mean, that's all right. Now, that said, right, being an online class, your quizzes and your tests are, of course, open note. But your work is going to be so much faster if you just memorize these things. You don't want to have to be looking this up, wasting time doing that when the clock's ticking. Okay, that is the end of 3.5. Very exciting.